Hi guys, in this video we're going to discuss a current carrying wire in a magnetic field. We'll talk about interacting magnetic fields, the interaction of a uniform magnetic field with a current carrying wire, the motor effect, and we'll finish with a summary.
In our video about electromagnetism, we learnt that when a current goes through a wire, then astonishingly, this will create a magnetic field. We represent this with these magnetic field lines. And these magnetic field lines are concentric circles centered around the wire. So here's something. We know that the current carrying wire is creating its own magnetic field. But let's imagine what happens if we put this wire inside another magnetic field. So here is our current carrying wire again. And we haven't drawn them in this picture, but this current is creating its own magnetic field, which are these concentric circles that go all the way round. But now we've decided to place our wire inside another magnetic field. And the field that we are looking at is being produced by the north pole of one magnet and the south pole of another. The main point here is that we have two magnetic fields in the same area, and these magnetic fields are going to interact with each other. Okay, so it's time that we learnt about what happens when magnetic fields interact with each other. In particular, what happens when two magnetic fields overlap. Let's imagine, for example, that we have one bar magnet on the left, and we know what sort of field it should create. And then we have another bar magnet on the right. And we know what kind of field that magnet should have too. But something we might be interested in is what sort of magnetic field do we see? What do the magnetic field lines look like when we bring the two magnets close together? To be able to understand or work this out, we need to learn a couple of rules. And it turns out that in places where magnetic field lines point in the same direction, they will add together. So let's imagine that there is a place where the fields overlap and they point in the same direction. Then in that case it should make sense that the fields come together to make a stronger field. And by drawing the magnetic field lines closer together on the right hand side, we have displayed exactly the fact that the magnetic field gets stronger. Now what about in places where the fields overlap and they point in opposite directions? In this case, they're going to cancel each other out. So imagine that the field lines due to one of the magnets points to the right. Imagine the field lines due to the other magnet point in the other direction. Then in that region, there should be no magnetic field, because the field lines cancel out. Now we won't try to understand the next part in too much detail, but for interest, let's take a look at the field due to two bar magnets which are nearby each other. Let's just remember what the field lines looked like for each magnet when it was on its own. For example, the magnet on the left hand side had field lines that were coming out of the north pole and then going into the south pole. And for the bar magnet on the right, we would again have field lines coming out of the north pole and into the south pole. In this section in the middle here, we can see that all the field lines from the two magnets point in the same direction, so they add together to make one much stronger magnetic field. And that's why all of the magnetic field lines in that region are all bunched up together. That represents the magnetic field being strong. Now let's go back to the thing that we were originally interested in, which was what happened when we put a current carrying wire and a uniform magnetic field. Now the diagram that we have on the left might look slightly strange, so let's explain this. This cross means that we're looking straight from the bottom of the wire up to the top. And of course, if you looked from directly above or below the wire, you would expect to see these concentric circles as the magnetic field. So what we have drawn on the left hand side is the magnetic field of a current carrying wire. On the right hand side is the uniform magnetic field. And we know it's uniform because the spacings between the field lines are the same everywhere. Now let's use our rules for adding together magnetic fields to see what happens when we put the current carrying wire in the uniform magnetic field. the two magnetic fields are going to add together to look at something like this. We see that the field lines are closer together over here than they are over here. Let's explain this a second. If we go back to our original picture, we see that these magnetic field lines here are going to point in the same direction as these field lines here, so they're going to add together to make a stronger field. Let's look at the bottom half of the picture, and instead these magnetic field lines point in the opposite direction to these magnetic field lines, so they will cancel each other out to make a weaker magnetic field. So that's why the magnetic field is stronger here and weaker here. So what does all of this actually mean for the wire? And remember, it's this here which is the wire. Now the field lines look kind of stretched here above the wire. And if you imagine them like rubber bands or something, then the field lines look like they're going to catapult this wire forwards. By forwards I mean this direction. To be more precise, there is a general rule which says that the field lines will always try to straighten out. Well, let's take a look at what happens when the field lines try to straighten out. We could straighten out this field line here by bringing it this way a bit. And in fact, to straighten out all the field lines, they all need to try to move this way. And this means there will be a force on the wire in this direction. The force that we've just explained actually has a special name. It's called the motor effect. We've learnt that a current carrying wire feels a force when it's in a magnetic field, and this is what we generally call the motor effect. As we saw on the previous page, the force turned out to be perpendicular to both the current and the magnetic field. So let's first show here it is perpendicular to the current, and then also perpendicular to the magnetic field. So when we put a wire in a magnetic field and it carries a current, it's going to feel a force and it's actually going to move. Let's look at some properties of this force. Turns out if the magnetic field is increased, then the force on the wire will also be increased. So here, by drawing more field lines closer together, we've represented a stronger magnetic field. And the result of this is that the force exerted on the wire will actually be larger. Rather than controlling that magnetic field, there's something else we could change. It turns out that if the size of the current through the wire is increased, then the force on the wire will again be increased. So this time we're back to the normal magnetic field. But this time we're putting a larger current through the wire. Then as a result of this larger current, there will again be a larger force on the wire. Now we mentioned already that the force on this wire is actually perpendicular to both the direction of the current and the direction of the magnetic field. So let's again draw in those perpendicular angles just to remind ourselves. Perpendicular to the current and perpendicular to the magnetic field. Now, if you remember Newton's third law, you might remember that every force should have an equal and opposite reaction force. So where is that force here? Well, it turns out that there will be an equal but opposite force on the magnets themselves, pushing them in the other direction.
Hey guys, I hope you enjoyed the video. If you're looking for an amazing GCSE Physics and Combined Science resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make physics at GCSE a walk in the park.